In this video, I want to prove a fundamental theorem from linear algebra, which is the diagonalization theorem. It's a well-known theorem, but I want to derive this theorem, want to prove it, because we will use it also in the next video when we discuss the proof of the singular value decomposition, the SVD. Now let A, and we'll put the tilde here to denote that this is a matrix, be an n by n symmetric matrix. This will be a real symmetric matrix. So we are going to restrict ourselves to only real matrices. We prove that A is orthogonally diagonalizable by induction on the size of A. So we want to prove essentially the following theorem, that A, this n by n real symmetric matrix, can be written like this. A matrix U times a diagonal matrix D, and here we have U transpose, and this product is equal to A, where U is an orthogonal matrix, so U transpose, or if you want U transpose U, this is equal to the identity matrix. Clearly, if we consider A to be a 1 by 1 matrix, so if we set n equal to 1, well, in this case we can set the matrix U equal to a scalar actually, so this will be a 1 by 1 matrix where the element is the only element is equal to 1, and the matrix D we can set it equal to the matrix A. So in this case this theorem holds trivially. You can see that of course in this case A will be equal to U D U transpose, but this is just trivial. We have proved it for n equal to 1, but we want to prove it for a generic n. Now, for the induction hypothesis, we can assume that every n minus 1 by n minus 1 real symmetric matrix is orthogonally diagonalizable. So if it's true for n minus 1 by n minus 1, we want to show that this is also true, this must be true for an n by n matrix as well. Now let's consider an n by n real symmetric matrix, and we call it A. Let lambda be an eigenvalue of A, and V be an eigenvector with eigenvalue lambda. Now we set also Q1 equal to the vector V divided by the mode of the vector V, and we are going to extend the basis which is made up only of this vector Q1 to the following orthonormal basis. So we are going to construct an orthonormal basis like this, made up of Q1, Q2, dot 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 Qn. So this basis is an orthonormal basis in Rn, if you want. Now we define the matrix Q, which is given by the first column. In the first column we put the vector Q1, so this is the first column, then we put in the second column Q2, and so on. In the nth column we put Qn, like this. Then if we consider the product between A and Q, this can also be written like this. So in the first column we have lambda, which multiplies the vector Q1, so lambda times the vector Q1. Then we have the matrix A, which is applied to the vector Q2 in the second column. Then in the third column we have AQ3, and so on. So in the nth column we have AQN, like this. So we can write it like this. And we can also write it in the following way. So this is also equal to the following. So we have the matrix Q, and here we apply this matrix to, in the first column, first row, we put lambda. Then here we put a 0, but actually this 0 here is not really a scalar. This is an n minus 1 by 1 vector. So here we have n minus 1 rows and 1 column. So this is an n minus 1 by 1 vector. Then here we have another vector that I will call D, and this is a 1 by n minus 1 vector. So 1 row and n minus 1 columns. And then here we have an n minus 1 by n minus 1 matrix, and we call it A prime, like this. So let me remind you that D is a vector like this, so it belongs to R to the 1 by n minus 1. Because as I said, D only has 1 row and n minus 1 columns. And of course, A prime will be an n minus 1 by n minus 1 matrix, so we can say that A prime belongs to R n minus 1 by n minus 1, like this. Now, since the matrix Q here is orthonormal by construction, because we are using the orthonormal basis Q1, Qn, then we can also write Q transpose A Q equal to the following matrix here, because basically when we multiply this matrix AQ by Q transpose on the left, here we have Q transpose times Q, and that's equal to the identity matrix because Q is orthogonal. So this will be equal to lambda D0 A prime, like this. Now we can take the transpose of this, and if we take the transpose of a product of 3 matrices like this, so we have A, B, C, and we take the transpose, a simple property tells us that we can rewrite this as C transpose, B transpose, A transpose. So by using this property, we can rewrite this formula here like this. If we take the transpose, we have Q transpose, A transpose, Q, and this is equal to, well, when we take the transpose of this, we get lambda, so this is just a real scalar, so when we take the transpose, lambda will remain there. Here we have D transpose, so we have this vector transpose. Here we have 0, and here we have A prime transpose, like this. But we know that A is equal to A transpose because, as we said at the beginning of this video, A is a symmetric matrix. It's a real symmetric matrix. And now what we can do is the following. Since this is true, then it means that this matrix here should be equal to this matrix here. Because if A is equal to A transpose, this will be equal to this, right? But now the equality between these two matrices implies that D should be equal to the 0 vector, because otherwise this will not be equal to this, or if you want, this will not be equal to this. And also we have to set A prime equal to A prime transpose. But now, since A prime is an n by 1 by n minus 1 matrix, we can apply the induction hypothesis. And it means that there exist matrices like this, Q prime, D prime, so D prime will be a diagonal matrix and Q prime will be an orthogonal matrix with dimension n minus 1 by n minus 1, such that A prime can be set equal to Q prime, D prime, Q prime transpose. And therefore, we can write Q transpose A Q. This is equal to, now remember that we have to set D equal to 0 here. We can rewrite like this. So lambda 0, 0. And here, instead of A prime, we put Q prime, D prime, Q prime transpose. Like this. We have to take the transpose here. But remember that A prime transpose is equal to A prime. So A prime is a symmetric. By the way, notice that in this case I have put the transpose here, but you can also write the same expression in another form. So you can define a matrix H equal to Q prime transpose, and therefore you can write A prime equal to H transpose D prime H, like this, where H also in this case is an orthogonal matrix, right? Because if we take the transpose of this matrix, which is orthogonal, we still get an orthogonal matrix. So if you want, you can also make this transpose operator appear on the left, but this is not important, and we define Q prime actually, not Q, in such a way that the transpose operator appears on the right. But this is not a problem. So we can rewrite A prime like this, and we can also rewrite this matrix in the following fashion: 1, 0, 0, Q prime, and then here we have lambda 0, 0, D prime, and then here we have 1, 0, 0, Q prime transpose, and we can also rewrite this matrix here like this. So we can put the transpose out of the matrix. We can put it here, because when we take the transpose here of 1, this is just a scalar, it will still be 1. Remember that this is not a scalar. In this case, this is just a 1 by n minus 1 vector, whereas this 0 here is an n minus 1 by 1 vector. So we have arrived at this point, and it follows from here that we can multiply on the left by Q here, and we can also multiply on the right by Q transpose. And remember that Q transpose will be equal to the identity. So you can also write A equal to Q. Then we can write the product of these three matrices. Let's rewrite it here. So we have 1, 0, 0, Q prime. Then we have lambda 0, 0, D prime. Then we have 1, let me do it properly, 1, 0, 0, Q prime transpose. And then remember that we also have Q transpose here. Now we can set, so we can call this product of matrices U. So this would be U. And this matrix here, we will call it D. And of course, here we have U transpose. So basically what we get in the end is A equal to U D U transpose, which is the theorem that we wanted to prove, but actually we still need to prove one last thing. So we need to prove that U is an orthogonal matrix. And how do we prove that? Well, it's easy. We simply have to take U and multiply it by U transpose. Or if you want, you can put the transpose here. So U transpose U should be equal to the identity matrix. So this should be an n by n identity matrix. Well, we still have to do the calculation, but after we do the calculation, hopefully we find that this is true, and therefore we will prove the theorem. So let's do this last computation. U transpose U is simply equal to 1, 0, 0, Q prime transpose, Q transpose. So this is simply the transpose of this, and of course it's equal to this. And then we multiply by U. So here we have Q, and then we have 1, 0, 0, Q prime here. But now you can easily see that Q transpose Q is equal to the identity matrix. So it means that we can write this as, we can also take the transpose. So here we have 1, 0, 0, Q prime transpose, and we have to apply this matrix to 1 0 0 Q prime like this. Now we can make this multiplication. We can carry out the multiplication, and we can write it like this: 1 0 0. Then here we have Q transpose, Q prime transpose, Q prime. And now we know that Q prime is an orthogonal matrix, and actually the product of these two will give me the identity matrix in the n-1 dimensional space. So this will be an n-1 by n-1 identity matrix. But now when we add this column and this row, we get the n by n identity matrix, and therefore this completes the proof, which we will use also in the next video to derive the proof of the singular value decomposition.